Hello everyone. In this video, we are going to learn how we can make simulations in with respect to the Oyster Rice game that we actually have played last time. So the last time we actually have done simulating the demands for just one single queue. So given some specific number for the queue, how we can actually derive the demand in simulation and how we can calculate the sales and the number of leftovers and also so that we can actually calculate profit. Okay. So for any given queue, we can find the expected profit, but to find out the optimal quantity, we have to do some kind of calculations like changing the number for Q and then going back to the simulation and observing what is actual not actual expected profit, right? So today in this video we are going to first look at how we can actually make that process somehow convenient and easier. Okay, so let me actually share the screen for the Radiant. Okay, so if you're using the Radiant, please open it. Okay, first, I have actually put the state file in your Dropbox folder that actually contains all the parts we have done last time. So let me actually open that state file for you. So to open the state file, we are going to choose the last option in load data of type, Radiant state file. So please choose it and click load. And then you can go to your data. So this is actually part of the lecture 5. And then you can actually go to the data. Then you must be able to find oyster rice state before repeat. So please open it. And then you can see that it automatically goes to the menu for simulation, which is actually located at under the model. And at the bottom, you can find the simulate. So last time, what I've done was actually this part for the simulate. If I'm going to give you a review, then it goes like this. So we first define what kind of variables we are going to use. So there are two different types. The first one is discrete. The second one is constant. So for the discrete, we have described the probability for each dice. So we have defined three dices. So dice one, dice two, and dice three. So as you can see, we have a dice one, dice two, and the dice three. I have put down, 0.166, but actually, you can actually put down 1 over 6. Actually, let me actually change it. Okay, I think this is somehow older version. So 1 over 6, 1 over 6, and 1 over 6, 6 times. Let me actually change it. Because this is a more exact probability. And then let me just copy these 1 over 6 part. Or let me just copy everything about dice 3. And then let me just copy from 1. This, okay. That's good. And then just paste it and paste it. So now, you can see that we have defined three dices, right? Because, in the previous, game that we have played, we basically simulate the demand by just rolling three dices and take the sum of three numbers on dices. And so this is how we are going to simulate the demand here. And then Q, as well as the price and the cost and the service value is defined here. So the Q is defined at 13 and then P7, C3, S1. So you just write down the name of a constant variable and then just a number, okay, and the semicolon. Then you can actually define constants here. So, okay, maybe let me just write down the whole thing, um, or so that you can actually think of the meaning immediately. So let me just Q just a Q. So then it means that I have to change this one. Uh, so let me just change into the demand, and then demand, and then Q minus demand. I'm just changing this. I mean, just to make sure you can actually follow the logic better. Okay, so profit is equal to minus cost times Q plus price times the sales. Because sales is equal to the pair mean of demand and Q. So basically, we are going to pick the minimum between demand and Q because Q is the quantity we are going to prepare. So when the demand is, let's say, bigger than the Q, then we can only supply up to Q. So the sales amount will be Q. Then S is actually the salvage value times, instead of P max, we can actually replace it by leftover. Okay. I mean, you can actually use the original state file as it is. That's fine. But I mean, changing it to make you understand clearly. Okay. So we have defined constant variables and discrete variables, and we have write down simulation formulas demand as the sum of each number on three dice, and then sales is given as the pair min, and the leftover is the pair max. Oh, by the way. And then profit equal to minus cost times Q plus price times sales plus average times leftover. Okay, that's good. So in this case, I mean Q is at 11. Oh, sorry, actually 13. Let me just change 11. I mean, it doesn't matter. So after you click on this run simulation, you can see the result. So as you can see, we have actually 1,000 simulations here. I mean, random seed again is defines the sequence of randomly generated numbers. I mean, you can just leave it as it is, 1, 2, 3, 4, 5, or 1, 2, 3, 4. It doesn't matter. It just gives us some different sequence of random numbers. And then you can see that what is the expected profit out of 1,000. So for each simulation, we are going to have one data for profit. So now we have a 1,000 simulations, and then we can actually calculate the average profit, right, per each simulation. That is 35.8. Okay. And then we try to find the optimal number of quantity that we have to prepare. Then we can change this, let's say, how about the 12? And then we just rerun simulation. Then we are going to have some new simulation result. And then expected profit is 36.07. So it has increased, right? And then let's actually increase a little bit further, 13. And then let's rerun simulation. Then 35.69. So it seems like, I mean, from 11 to 12, it has increased, but from 12 to 13, it has decreased. Okay. So 12 seems to be the one that will maximize expected profit. Okay. So this is how we can actually figure out the the kind of optimal number of quantity that we are going to prepare to maximize the profit. However, it's somehow cumbersome in the sense that we have to change the Q each time and check what is the expected profit. So today, let's actually learn how we can use this repeat tab to figure out the optimal quantity right away. So let's go to the repeat. And then we are going to define what variables we are going to resimulate. And if you click this one, then they're actually the variables we have defined. The salvage cost, price, and Q, those are basically the constant variables we have defined. And then dice is basically is a discrete random variable. So each when you roll each dice, we can have the number between 1 and 6 with the equal probability. Do we have to resimulate this? If we are going to, let's say, resimulate the dice 1, what happens is this. So in the previous tab, we have simulated demand 1,000 times. If we are going to resimulate dice 1 or dice 2 and dice 3 at the same time, then we are going to generate the next set of 1,000 simulations when we try to evaluate different choice of Q. Is this fair of comparison? In terms of comparison, it's not fair because, I mean, we are going to see that pretty soon. So what I'm going to do is we are going to start from 3 for the Q. And then we are going to check the expected profit for the case when Q is equal to 3, and then Q is equal to 4, 5, 6, and up to 18. So if we are going to regenerate the demand for each Q, then basically we are going to evaluate expected profit of each Q when actually demand itself will be different. So that is not a good way of comparing the expected profit for all different kinds of Q. So what I have to do in this case, actually, we should not resimulate any of these demands, right? So no variables will be resimulated. And for the output variables, so basically, I mean, if you are going to write down some variables as part of this repeat simulation formula, you have to define here first. So obviously, we are going to change the queue. So we need the queue information, and also, I mean, we are going to basically pick queue according to the expected profit. So we have to define the profit. And also, I mean, let's actually add the sales and then leftover, okay, to see what is actually the sales for each simulation so that eventually we are going to look at what is expected sales for each queue and what is expected leftover for Q. By the way, here the sales is different from, I mean, expected sales is different from expected demand. According to the demand distribution, in this case, if you take actually the sum of three numbers on three dices, then it actually is a discrete version of normal distribution. And then the expected demand would be basically about, in this case, I mean 10.5, right? However, 10.5 is not the same as expected sales. Why? Because expected sales is actually dependent on how many oyster rices we are going to prepare. So let's say, I mean, if we, let's say, prepare only the 10 oyster rices, and then even when the demand is 10 or 11, 12, 13, the sales would be the same as 10. So expected sales tend to be less than expected demand. So we want to know what is expected sales. And then for the group by, we have to choose repeat because we are going to repeat this process from Q, from 3 to 18 in terms of Q. So if you choose a repeat, then automatically you are going to see this grid search. And here you are going to find basically what kind of range you are going to use for repeat. So in our case, we are going to use this Q from 3 to 18 so that we are going to look at the result. Okay. So first, okay, one more thing is that we have to define what kind of function we are going to use. So in this case, we are going to use the mean, right? That's the average because we are going to check the uh, average profit of or the mean profit of each Q. So we are going to apply the function that is a mean. And the random seed, you can just leave it as it is, like 1, 2, 3, 4, or any other number that is fine. And the number of repetitions, you don't have to worry about. It will be automatically determined. So in this case, we are going to check from 3 to 18. So automatically, number of repetitions would be 16. So, but you don't have to write anything. And then the data will be stored at the simdat underbar repeat. Okay, so let me just write down the repeated simulation formula here. So we want to find the Q that will maximize expected profit, right? So we want to find the optimal Q, and then we are going to use the function called the find the max, and then we want to maximize the profit, right? In terms of Q. So when you use this function, find the max, you first write down what is the objective function and then what is the decision variable as a second one. Okay, but when you just write down like this, if you click this repeat simulation, then there'll be some matter. Okay, please provide a simulate data set as input. So uh, the problem actually, comes from the fact that we have to actually put down underbar and mean after the profit and after the Q. Okay, then it's done. Okay. Then you can see that the ultimate Q is actually the 12. Okay. So we have a number of observations will be 16. And then for each leftover profit mean, the Q mean, it just shows basically the average of all of these 16 observation. This information is not that much meaningful. It's not that much meaningful in this case. So what is actually meaningful is actually by going to sim that repeat. Okay. Okay, anyway, let me actually save this as a save file. So in Radiant, to save it as a save file, we are going to use this disk button. So let's just click this one and then click the first one, save Radiant save file. So and then let me just write down Oyster Rice state. Maybe just write down after repeat and the save it. I'm going to actually post this into your Dropbox folder later. Okay. Okay, so this is how we can find the optimal Q. And then actually, let's see what happened to this data set. So let's go to the data and then sim that repeat is here. Then let's actually go to the view. By the way, for this gradient, the manis actually shows only the 10 out of the total rows, and then it shows some information related to the data. So in this case, automatically it shows what kind of formula we have used to generate the demand, the sales, leftover, and then profit. Okay. So let's go to the view. Then we can actually see all the data that we have for this sim that repeat. And then the first column, that rip is actually just shows what actually Q we have used. So it's not that much meaningful here. So let's just use the Q mean, profit mean, sales mean, leftover mean, only these four, because we know that the optimal Q is actually equal to 12. So now from this one, you can see that, okay, if we have prepared, let's say, three oyster rice, mm, that's actually, the smallest demand that we can have. And then profit is 12. And then mean expected sales is the three, because we can only sell up to three, right? And then there's no leftover. If we prepare, let's say, the 9, and then this is the expected profit, and the expected sales is 8.48, and then the leftover is only 0.52. And then let me actually, show all of them, show 25 entry that it shows all of them. Then you can see that, for instance, if we prepared 14, then the expected sales would be 34.75. The expected sales would be 10.46, and 3.54 is the expected leftover. Okay. So one thing that we want to look at, for instance, we want to look at the graph that shows how actually expected profit changes over Q, right? So let's actually draw it. So let's go to visualize, and then okay, let me actually uncheck this filter, because all the cases profit is positive anyway. So let me actually check this line as plot type. And for the y variable, let's choose profit mean. And for the x variable, let's choose the quantity. So Q means just the quantity, the same thing. And then this actually plot shows us how expected profit changes as Q increases. So as I've told you, Q increases from 3 and up to 18. And then this shows the typical like concave function, right? So when it first starts, it starts to increase. And then that increase amount marginally starts to decrease. And it will reach zero at this point. And then it actually gets negative. So that expected profit actually goes down. And then this value is actually 12. You can also draw other actually graphs such that not only the profit, but also sales mean and then leftover mean. Update the plot. Then it shows not only the expected profit, but also expected sales and also expected leftover. Okay. So the problems that you are going to do with respect to this optimal product availability is actually homework 3. And we are going to analyze the case in a textbook by using R or Radiant. So if you're going to use Radiant to do that homework, then you can actually use this feature to provide the graph of expected profits, sales, and leftover as Q increases. Okay? Okay, this is actually kind of end of it. I have shown you how we can use the repeated tab to actually find the optimal number of a Q. And I have also shown you how we can visualize expected profit, sales, and leftovers in terms of Q. Okay? Okay, thank you for watching.